Typically in harmonic motion you have some kind of second order differential equation, which usually takes the form of this. Don't worry too much about what the variables are, but when you solve this, as you'll know, if you have this as an imaginary root from the auxiliary equation, then it'll come out with something like e to the t sine t plus cos t, just making up an equation. And obviously that will oscillate, but then it'll come towards like a equilibrium point. With resonance, however, you've got d squared x dt squared plus k dxt. But it's equal to some kind of external force. So f of t, so an f of t could be something like sine t or cos t or something like that. So effectively, when this driving frequency, which is providing like an additional sort of force, is less than the resonant frequency, then the system will just sort of keep going backwards and forwards nicely at pace. But when it gets much greater than the resonant frequency, then the system's going backwards and forwards so frequently that it can't keep up, and this causes quite a lot of problems with the amplitude increasing so violently. And obviously this causes problems with like bridges and stuff if it's like just oscillating so much that it effectively destroys itself. I think the best example is the Dakota Narrows bridge, if you've seen that. And I think that's generally what you need to know in terms of theory for it. Okay.